So nothing too fancy today. We're going to be talking about more double integration. Okay. So call this double integration over elementary regions. Okay. So previously, let me show this. Remember what we did last time. We talked about integration over rectangles. Right? It turned out that if the region that you're integrating over was a rectangle, then you could split it up into two single integrals, right? And those two single, if this is say AB, CD, then your double integral over the rectangle could be recognized either as integrating over x first and then y, or integrating over y first and then x, right? As long as the function was continuous. So we're just going to do something slightly more complicated than that, and we'll do regions that are not rectangles, but they're just slightly more complicated than rectangles. Okay. So here's the definition. So if the region, we're gonna classify the regions over which we're going to integrate. So if the region can be expressed, and this will seem simple, but once we get to more dimensions, then it'll be a bit more complicated. So try and get this idea. If the region can be expressed as like this, xy in R2, where x is constrained to lie in some interval, and y lies between two functions of x, phi1 and phi2, where phi1 and phi2 are continuous functions. Then we call D an x-simple region. An x-simple region. Okay, so the picture you want to have in your head is like this. There's some on the x-axis. There's some interval. AB, and then you have these two functions, phi1 and phi2. So this is phi1, this is phi2. Right. So here's the y. And so for each fixed x, right? For each x, the region lies between phi1 of x and phi2 of x, right? So it's all it's this region here. Okay, so this is D. This is D, and you see that D is simple in the sense that the x values range from A to B, x values range from A to B. And the y values depend on x and lie between two functions of x, like a low function and a high function. Okay. So maybe a simple example, you have like your low function is say x squared. Your high function is x, and you're on the interval x lies between 0 and 1. So then your high function is going to be like this, your low function looks like this, and this region between it is D. Right? This region between it is D. Right. Okay. And this is So this is, you have a way of describing the region that is simple with respect to the x coordinate. Actually, this one is also simple with respect to the y coordinate. But let me just ignore that for now. Okay, you guys, do you see what I'm talking about when I say an x simple region, right? It's nothing fancy. You have a, b, and you have one function, and you have another function, right? And D is the region between D is the region between those things. Okay, so that's called x simple. Okay, and you could have you can similarly we can define a y simple region similarly for y simple regions. Right, a y simple region is going to be something like where you have y ranges between c and d, right? And you have some function, you have one function of y, and you have some other function of y, right? And you have your region is the space between those functions. So this is like this. Okay, so here's the point. If D is, say, x simple, then the integral over D you can realize as a double integral, as two single integrals. It's going to be the integral from a to b with respect to x of the integral from phi1x to phi2x of f of xy d1. Okay, so let me do an example first. Okay, so let's do an example. So here's our region. Somebody gives you a function. Your function is, say, f of x1 is x squared y. Okay. And then they give you a region that they want you to integrate that over. And the region looks like this. 1, 2, 3, 4. Here is 1. So okay, so this function here is 4 minus x squared. And then you've got another function going up like this, y equals 3x squared. Okay, so you've got these two functions. Right? And somebody says, I'd like you to integrate this function over this region. And if you integrate this function, right, f of x, f of y is x squared y, and if you integrate it over this region, right? So the picture in your head is like this, right? This thing is lying down, right? This thing is lying down on the ground here, right? You have this is your domain of integration, and then you have your function floating over it, right? And you're finding the solid that lies underneath, that lies over this thing and under the graph of the function. Okay. And what the theorem says is that the integral of x squared y over that thing, you can calculate. So we're gonna consider this thing as an x simple region, right? X's range from 0 to 1, and the y's, as you see, range between two functions of x. Right? You've got one function of x, and you've got another function of x, right? So this is going to be the integral. The x's range from 0 to 1, and the y's, the range of the y's depends on the x's, right? It'll range from 3x squared up to 4 minus x squared. Right? You get integrating this function between there and there. Okay. And so you've got these, now you've got this double integral, and you just integrate it, right? So you integrate this first thing with respect to y. Well, so you're looking at this thing and say, well, I can, this x squared is a constant with respect to y, so I'm going to pull it out. So I'm going to pull it out. Here I'm going to have x squared integral from 3x squared 4 minus x squared y dy dx. Okay. And then you just integrate that. You know, the integral of y is of course y squared. Right? So you get the integral from 0 to 1 x squared y squared over 2 between 4 minus x squared over 3x squared dx. Right. So that gives you the integral from 0 to 1 of x squared times 1/2 of 4 minus x squared squared minus 3x squared squared dx. And then you multiply this out, and then you integrate it from 0 to 1. I'm not going to do it. I assume you guys can do this. Yeah, it's Calc 1. Is it clear how to do these sorts of things? Right? Like somebody, you're trying to integrate a function over this domain. You recognize the domain is an x-simple region, right? It's just the x's range over something, and the y's range. The range of the y's depends on the x, right? It's going to be ranges from one function of x to another function of x. You say, oh, okay, this is x-simple, right? Once you realize it's x-simple, then you set it up as in the right way. Right? You're going to integrate over the x's, right? You integrate with respect to x from 0 to 1, and the y's depend on x. Okay. You don't put it in the opposite way, right? If you wrote it in the opposite direction, it actually wouldn't make sense, right? Because if you wrote something like this, squared y dx dy, that actually wouldn't make any sense, because once you integrate this, once you do this inner integral, there would be no more x's, right? And then what are you integrating between, right? What does this mean to integrate between 3x squared 4 minus 4 to 4 minus x squared? It doesn't make any sense anymore, right? So it'll be clear what order to put it in based on what kind of region you have. Okay. Let me ask you to do one. Do a couple, actually. So here's one. Maybe just, I'd like you to set it up. So here's the region. Like this. This line here is 2x plus y equals 2. Okay. And yeah. So I want you to set up an integral. So set up, you have some function. Doesn't matter what the function is. It's just going to be f. Okay. You're integrating it over d. This region is actually expressible as an x region, or as a x-simple region, or as a y-simple region. So first, I'd like you to set it up as an x-simple. I'll give you the bounds. This is 0, 1, 0, 2. First, I'd like you to set it up as an x-simple region, and integrate it, or just set up the integral, right? And then I'd like you to set it up also as a y-simple region. It should take you about 1 minute or 2 minutes. turn to somebody next to you and say, what are the bounds of your integrals?
It's like it's not a rectangle, so now you can just do two separate sections. So I
Well, then it's
and you express this line either in terms of y or in terms of x. So you do x boundaries and then the y boundaries go from 0 to x. Or you do the y boundaries.
Okay, so so you have this region D, right? And it can be expressed either as an x simple region or as a y simple region. Let's express it first as an x simple region. So what's the range of x? 0 to 1. 0 to 1. What's the range of y? What's the range of y? Well, it depends on x, right? But the lower bound is always 0, right? So y always starts at 0, as we see. And the upper bound is going to be dependent on x, right? If this is x, what is this height here?
2 minus 2x.
It's going to be 2 minus 2x, right? Because y is 2 minus 2x, right? If this is x, the height is 2 minus 2x, right? So for each x ranging from 0 to 1, we look at the y's range from 0 to 2 minus 2x, right? And so when we set up the integral, right, it's going to be x ranges from 0 to 1, and y ranges from 0 to 2 minus 2x. So the double integral is that. Okay. If we set it up in the opposite direction, right, x, y ranges from what to what? Any good? 0 to 2, right? 0 to 2. And then somebody else, what's for each y, right? If we fix a y, what's the range of x? What's x going to be? Well, somebody else? Anybody else? Laura.
Would you, is it, I just have it somewhere. Was it like 1 minus y over 2?
Yeah, let me think. So let's see. If we know the y, we're trying to figure out the x, right? So we're trying to figure out the x. So 2x is 2 minus y. So x is going to be 1 minus y over 2. Yeah, 1 minus y over 2. Right. So, right. And the y's range from 0 to that number. So, I'm sorry, the x's range is from 0 to that number. 1 minus half of y. Right, and so we could just as well have calculated the integral by integrating over x first, right? Integrate from x equals 0 to 1 minus y over 2, and then integrate from y from 0 to 2. Okay. Okay. So nothing. Yeah, it's not that exciting. Hold on.
What then is f of x, y?
It's just some function. If you like, I could have given you a function. Say cosine x.
So you can't know the function from the graph?
No. This is just the domain of the function, right? The function is a function of two variables, right? This is the thing that's lying flat here, right? This is your d, and then above the function, above that thing, you have some function, say, right, floating over the function, and you're calculating the volume. Yeah, people often get confused. They're like, "Where's the function?" Or like, because you're thinking in one variable in the one variable setting, right? But this is the domain.
Okay.
Yeah, this is the domain that's lying flat in the plane here, and the function's floating above it or below it. Okay. Just one comment. You notice that we integrated this one as an x simple region, but we could have actually integrated as two y simple regions, right? We could have broken it. We could have said from here to here, right? We'll take y goes from 0 to 3, right? And then y goes. We could break it into two y simple regions, d1 and d2, right? Where in the first one, d1, x, y ranges from 0 to 3, and x ranges from what to what? For each y, the x's range from 0 to something. What's that something? The square root of y over 3. Okay. Right, so that would be d1, and then the second region would be y goes from 3 to 4, and x goes from what?
The square root of 4 minus 1.
Right, the square root of 4 minus 1. The square root of 4 minus 1, which is positive since y is between 3 and 4. Okay, so we could have instead of doing this integral, right? We could have instead written x squared dA d as going from dy and then dx 0 to 3, and then 0 to root y over 3, right? Plus double integral x squared y dx dy. Y is good from 3 to 4, and then x goes from 0 to the square root of 4 minus y. Okay, which do you like better? I know, probably you like that one better. I do, right? So there's some choice involved. Right? You can, part of the game is how do you want to split up your region, right? If, for example, I said I'd like you to integrate over an annulus, right? A difference of circles, right? A difference of circles. Well, then it's kind of a pain, but you could say, well, I'm going to break this annulus up into parts, right? Here I've got an x simple region, here I've got an x simple region, and then this thing is x simple and this thing is x simple, right? So I could break it up into 4 x simple regions, right? Or I could have done it into 4 y simple regions. Right? Now I've got this is y simple, this is y simple, this is y simple, this is y simple. Right? So you can take complicated things and then break them up into x. That's the point of these simple regions. That often you can take complicated regions and break them down into these things where the integral is easy. Okay. Any questions? Any questions? It's pretty straightforward. So. Let's see. Okay, so there's a trick of integration called changing order. Of integration. And it's basically doing what we just did. Somebody gives you an integral and says, try and integrate this. And it turns out to be very hard one way, or even impossible that way. Okay, it might be that the integral is impossible. However, you recognize that you could express it in a different way, right? As say a y simple region rather than an x simple region. And it turns out that the integral is better that way. Okay, so let me give an example. So here's the point. Some regions can be expressed in multiple ways. often, or I should say sometimes, in this section, of course, it occurs 100% of the time. Sometimes the integral is easier one way. Okay. So here's the example. Somebody gives you this double integral, y squared 4. Somebody gives you something like this. Okay. It's iterated single integrals and says, oh, please integrate this for me. Okay. Just using calculus 1, it's hard to do. Right? You say, oh, I'm going to integrate, first I'm going to integrate this guy in the middle here. So I need to integrate x squared, cosine x squared. What's the integral of cosine x squared? Right, exactly. You should be shrugging. There is no simple way to do this. Okay. However, we're in Calc 3, and so we say, okay, I actually recognize this thing. This is actually equivalent to some area integral, and I can change the order. So what region are we dealing with here? Well, what's our domain? Well, y is going from. Do you want to take a minute and see if you can write down the domain? Take 30 seconds. Draw the domain. And then another 30 seconds and express it as an x simple region rather than as a y simple. Groaning because I'm in pain, not because of you guys. What terrible students. Yeah. Okay, turn to somebody next to you and say how you re-expressed it. Okay, anybody want to give it a shot? And then you guys, I think, know the answer. I want somebody who feels uncertain. Anybody feel uncertain? Sydney, how about you? You look a little nervous.
Yeah, I'm uncertain.
Great.
Okay.
Okay, so the y, just think, the y's range from 0 to 2, right?
Uh-huh.
And then for each fixed y, the x's range from y squared up to 4. So think like when y is 0, the x range from 0 to 4, right? When y is 1, the x goes from 1 to 4, right? When y is 2, the x goes from 4 to 4, right? So, right, we're always going from the x, you need to look at x equals y squared, right? X is going to go from y squared up to 4. Like here's the top, right? We're always going to go up to 4, right? and our lower bound is going to be y squared, right? The x is going to be y squared. So what does it look like? X is y squared. Is that
Square root x.
yeah, square root x. Y. If everybody likes to think in the opposite way because of prejudice. We all think, oh, y equals square root of x, right? But really, this is just as simple. Right, so we go from here to here. Right, so this is our region. Right, this is D. Okay, so this is D. Okay, so let's rewrite that then in terms of as an x simple region. Right? So what's the range of x? 0 to 4. X goes from 0 to 4. And then again we think for each y, what's the range of x? Well, right, for each, if I fix y here, right, then the x's range from
0
to
square root of x.
we're all prejudiced towards x over y, right? We all like x better than y. I'm afraid. That's wrong. Okay, so that means that we can rewrite this thing, right? We can rewrite this as a double integral. First, the outside is going to be x from 0 to 4, and the inside is going to be in y from 0 to root x. Right? And we have y cosine x over here. Right? This looks a lot more promising, right? Because we're just integrating y here. Right? Cosine x squared is a constant, right? So we can pull it out. So we get cosine x, the integral of y dy from 0 to root x dx, right, from 0 to 4. Then we end up with, right, this is going to be y squared over 2 cosine x, y squared over 2 between 0 and root x dx 4. Right? So we get cosine x, and here we get x over 2 minus 0, which is good. Right? X squared, sorry. X squared. X 0, 4. Right? And this is good, right? Because now, right, what's this? What's the integral of x squared, cosine x squared x over 2? Sine x squared. The derivative of that would be cosine x squared times 2x. Right, so we get a 4. We get a 4. We get a 4. Go back to calculus 1. No, just kidding. You don't have to. Okay, so this is going to be 1/4 sine x squared between 0 and 4, right? And then you just divide. Right. At some point I will make a mistake and you can tell me to go back to calculus. Okay, right, so this is good, right? This is very good because you have this impossible integral, right? Which in calculus 1, if somebody said, oh, you just iterate your integrals, you'd say, I'm stuck. By one variable methods, I can't do this, but you recognize this thing as an area, this is an area integral, and an area integral for which we can switch the order of integration. We switch the order, it turns out it's easier that way. Okay? And now it takes an impossible integral and turns it into an easy integral. Okay. Questions? Any questions? Okay, let's see. Let me, too much time. So, let's see. Okay, let me not do another example, but give you an important theorem that's in this section. So here's an important theorem in this section. It's called the mean value theorem. Mean value mean value theorem for double integrals. Okay, here it is. You have f, it's on some one of these x simple regions or y simple regions, and it's a continuous function. Then, so B is closed and bounded. So you have a continuous function, then in fact, there exists a point, x naught, y naught, in D, where the average value is attained, where the mean value is attained, where this is the area of D. So there exists a point where the mean value is attained. Let me explain this term here. Think about if I took the integral of a function from a to b dx, and I divided if I took what is let's consider let's look at this let's look at this term. So if let's consider in one variable, say the integral of your function over some interval and then divide by the length of that interval, right? What is that? Got a, b, right? I get some area here, right? I get some area here, and then I divide by the length of the base here, right? That is going to give me the average height, right? That'll give me the average height of my function. Okay. Similarly, for this thing here, right? I have some region D here, and I have some volume above it, right? And I divide that volume by the area of the base. I'm going to get the average height. Okay. So the mean value. So what this theorem says is that there is some point where the mean value actually occurs. Okay, like the mean value in this one variable picture, right? The mean value is somewhere around here, and indeed, right, there is a point where the mean value is hit. So this is the mean value theorem for integrals, for double integrals. Let me see if I can explain it to you in the couple minutes that are left. So think like this. Think like this, yeah. So I'll explain this to you next time. So instead, let's do one more example of the change of order. Okay. Sorry. Okay, so here it is. I don't want to rush it. So here it is. Again, something that looks very bad for you. Somebody gives you this awful looking integral and says integrate. Okay. But you are not intimidated. You know that it's going to work out very easily. So the main thing, of course, is looking at the domain recognizing what the domain is, and then switching it over to an x-simple region in this case, switching the order. Okay. Would somebody like to try it? Really?
So the graph is y equals sine x.
Yeah, y equals sine x. Y equals sine x. Or x equals sine inverse y.
Yes.
Okay, and so let's rewrite this thing. Right. We do the x's first. Well, it'll be from what to what?
From 0 to pi.
And then the y's go from
Sine x to 1.
sine x up to the x's from here. The x's go from 0 to pi over 2. So for each fixed x, the y's go from. Oh, I'm sorry. Okay, let's think. Let's be careful here. So y goes from 0 to 1, and x goes from sine inverse y up to pi over 2. So we're actually on this part here, Lily. You see that? This is the region. This is the region. I think you're thinking that this is the region.
Oh. Okay.
Right. So let's rewrite it. Right. Let's rewrite it. Right. So the x is right. X goes from 0 to pi over 2, and the y's go for each fixed x. The y's go from what to what?
0 to sine x.
0 to sine x. Exactly. 0 to sine x. And e equals sine x. Right? And the good thing is that we can pull that out, right? And then when we integrate, we get a sine x, and that's good because then we've got e cosine x times sine x, and we can integrate. Right? So when we integrate, right, we pull this thing out, we get the integral from 0 to pi over 2 of e cosine x sine x dx. And the antiderivative of that is just e to the cosine x. So we get e to the cosine x value between 0 and pi. Okay. Okay, so just a nice trick, a useful trick.